Imagine standing in your kitchen and plugging a toaster into a wall outlet, or watching an electrician connect a thick copper wire to a metal grounding rod driven deep into the soil beside a house. Look up, and you'll see towering transmission lines stretching across the landscape, each one connected to the earth in carefully designed ways. Whether it's a household outlet, an electrical panel, or a massive power substation, the same advice appears everywhere. Ground it. Connect it to earth. Electricity goes into the ground. We've heard these phrases so often that they sound almost self-explanatory. Yet they quietly hide one of the most misunderstood ideas in electrical engineering. If electricity really goes into the ground, then what happens next? Where does it actually go? At first, the question seems almost too simple to ask. After all, millions of homes around the world are connected to grounding systems. Every day, electrical faults, static charges, and even lightning strikes send current toward the earth. If that happens continuously, why doesn't the ground become filled with electricity? Does electrical charge accumulate beneath our feet over time? Does it somehow disappear once it reaches the soil? Or is the entire picture we've imagined fundamentally incomplete? These questions challenge an assumption that many people have carried since childhood, because the language we commonly use about electricity often simplifies ideas that are much more precise in engineering and physics.
The surprising reality is that the Earth is not simply a giant sink that swallows electricity. In fact, describing grounding that way can lead to misunderstandings about how electric current behaves. Current does not flow simply because a wire touches the ground. It flows only when there is a complete electrical path and a difference in electric potential that drives charges through that path. Without those conditions, no continuous current exists, regardless of how many grounding rods are buried in the soil. This distinction may seem subtle, but it is the foundation of nearly every electrical system used in homes, factories, hospitals, and power grids around the world.
Over the next few chapters, we'll build that foundation step by step. We'll examine what engineers actually mean when they use the word ground, why electricity flows only under specific conditions, and why the Earth does not literally consume electrical energy. We'll also explore why lightning behaves differently from the electricity powering your home, and why grounding systems remain one of the most important safety features ever developed. By the end, the answer to our original question will turn out to be both simpler and more fascinating than it first appears. The electricity doesn't vanish beneath the surface of the Earth. Instead, understanding what truly happens reveals one of the most elegant principles governing every electrical circuit, from a small household outlet to the largest power transmission network ever built. One of the most persistent misconceptions about electricity is the idea that it naturally wants to flow into the earth. It's an understandable conclusion because grounding is mentioned so often in discussions about electrical safety, but it isn't how electric current actually behaves. Electricity has no preference for moving downward, upward, or toward the soil. Instead, current flows only when a complete circuit exists between 2 points with different electric potentials. In other words, electricity is not searching for the ground. It is searching for a continuous path that allows charge to move from its source and ultimately return. Without that complete path, no sustained current can exist, regardless of whether a wire is touching the earth. A simple battery and light bulb demonstrate this principle remarkably well. Connect one terminal of the battery to the bulb with a single wire, and nothing happens. The battery contains stored chemical energy, and a voltage difference exists between its terminals. Yet the bulb remains dark because the circuit is incomplete. Add a second wire connecting the other side of the bulb back to the battery, and the light immediately turns on. The electrons are not disappearing into space or into the ground. Instead, the electric field established by the battery drives charge through a closed loop consisting of the source,
the electrical load, and the return path. Remove any part of that loop, and the current stops almost instantly. The electrical system inside a typical home follows exactly the same principle, although on a much larger scale. Under normal operating conditions, current leaves the utility transformer through the hot conductor, travels through an appliance such as a toaster, refrigerator, or computer, and returns to the transformer through the neutral conductor. That complete loop allows electrical energy to be delivered continuously. Throughout this entire process, essentially none of the operating current is intended to flow into the earth. The ground beneath your house plays almost no role in powering your television, charging your phone, or running your washing machine. Every everyday appliance depends on a closed circuit, not on the soil outside. This is why the grounding conductor found in modern electrical systems is better understood as a safety pathway rather than a working pathway. During normal operation, it carries little or no current. Its purpose is not to complete the everyday circuit, but to remain available if something goes wrong, such as damaged insulation, or an internal fault that energizes exposed metal parts. By separating the normal return path from the emergency safety path, electrical systems become both reliable and significantly safer. Once this distinction becomes clear, one of the biggest myths surrounding electricity begins to disappear. Ground is not the destination that electricity is trying to reach. In most situations, electricity never intends to go there at all. It simply follows the complete circuit that engineers have deliberately designed for it. If the normal flow of electricity never depends on the earth, then why is nearly every modern electrical system connected to it? Why are grounding wires attached to wall outlets, electrical panels, transmission towers, transformers, and the metal frames of appliances? The answer has very little to do with making electricity work, and almost everything to do with making electricity safe. Grounding is not part of the normal operating circuit for most household equipment. Instead, it exists as a carefully engineered backup system that remains almost invisible until something goes wrong. Consider a metal washing machine connected to a standard household outlet. Under normal conditions, the hot conductor carries current into the motor and electronics, while the neutral conductor returns it to the utility transformer. The metal exterior remains at essentially the same electrical potential as its surroundings, making it safe to touch. But imagine that the insulation inside the machine fails, and the hot wire accidentally contacts the metal housing. Without a grounding conductor, the entire metal case could become energized at approximately the supply voltage. The appliance might continue operating normally, giving no obvious warning that its exterior has become dangerous. Now imagine someone touches that energized metal case while also standing on a conductive surface, such as a concrete floor, damp ground, or plumbing-connected fixture. In that moment, the person's body may provide an unintended path for current to flow. The amount of current depends on many factors, including body resistance, contact conditions, and the characteristics of the electrical system. But even relatively small currents passing through the human body can interfere with muscles, breathing, or the heart. This is precisely the situation that modern grounding systems are designed to prevent whenever possible. A grounding conductor provides a much lower resistance path back toward the electrical source than the human body typically can. When a hot conductor contacts grounded metal, a large fault current can flow through the grounding system. That sudden increase in current is exactly what protective devices such as circuit breakers or fuses are designed to detect. Within a fraction of a second under properly designed fault conditions, the breaker disconnects power, removing the dangerous voltage from the appliance's metal frame before someone is exposed to it for an extended period. Grounding itself does not eliminate the fault. Rather, It creates the conditions that allow protective devices to respond quickly and effectively. This is why electrical engineers often describe grounding as a safety system instead of a power delivery system. It is not there to operate your refrigerator, computer, or microwave. Those devices function perfectly through the hot and neutral conductors alone. The grounding conductor waits silently in the background, carrying little or no current during normal operation, yet becoming essential during abnormal conditions. Its true purpose is not to send electricity into the earth, but to provide a predictable, low-impedance fault path that helps protective devices disconnect dangerous circuits before electricity can choose a far more hazardous route through the people those systems were built to protect. At this point, one question naturally follows. If ordinary electrical current doesn't simply flow into the earth, then what about lightning? Every thunderstorm seems to show enormous bolts striking the ground, trees, buildings, and power lines. It certainly looks as though the earth is absorbing vast amounts of electricity. In a sense, that observation is correct, but not for the reason many people imagine. Lightning is not drawn toward the ground because the earth somehow attracts or consumes electricity. Instead, it is driven by an extreme difference in electric potential between regions of a storm cloud and the surface below, or sometimes between different parts of the cloud itself. Inside a thunderstorm, collisions between ice particles, water droplets, and hail separate electrical charges, producing regions with very different voltages. Although the exact details of charge separation remain an active area of atmospheric research, scientists broadly agree that thunderstorms can create potential differences reaching hundreds of millions of volts. As that electric field strengthens, the normally excellent insulating properties of air begin to fail. The air becomes ionized, forming conductive channels through which current can suddenly flow. What appears as a bright lightning bolt is actually the visible result of this rapid electrical discharge as the atmosphere temporarily transforms into part of a complete circuit. When the lightning channel finally reaches the ground, an enormous current travels through that path for only a fraction of a second. But the current does not stop at the point of impact. Instead, the electrical charge immediately begins spreading through every available conductive material. It moves into soil, rock, groundwater, tree roots, buried pipes, reinforced concrete, utility grounding systems, and metal structures. This process is known as charge redistribution. The electrical energy is dispersed across an enormous interconnected environment until differences in electric potential are dramatically reduced. Nothing mystical occurs beneath the surface, and the Earth is not storing the entire lightning bolt as if it were filling an underground battery. A useful way to picture this process is to imagine pouring a few buckets of water into a massive lake. The added water certainly enters the lake, but the lake is so large that its overall level changes by an amount too small to notice. The Earth behaves in a similar way electrically. Because of its immense size and conductive connection over large regions, it serves as an enormous reference that allows charge to spread over a vast area. The electrical charge has not disappeared. It has simply been redistributed until the local voltage differences become much smaller than they were during the lightning strike. Understanding this distinction reveals why lightning appears so dramatic while remaining entirely consistent with the same physical principles that govern every other electrical circuit. Even one of nature's most powerful electrical events is not an exception to the rules. It is simply an extraordinary example of them operating on a far larger scale. We've now reached the question that inspired this entire discussion. Where does grounded electricity actually go? The answer is less mysterious than it first appears, yet it reveals one of the most fundamental ideas in electrical engineering. Electricity does not accumulate underground as though the Earth were an enormous storage tank. There is no hidden reservoir beneath our feet collecting electrical current from every home, every power line, and every lightning strike. The ground is not a hole that swallows electricity.
Nor is it a place where electrical energy simply disappears. Instead, it serves as a common electrical reference, a vast conductive body that helps establish a stable voltage reference for countless electrical systems, while also providing a reliable path for fault currents under specific conditions.
To understand why, it's important to distinguish between electrical charge and electric current. Current exists only while electric charge is moving, because of a difference in electric potential. As long as a voltage difference is present and a complete conductive path exists, charge continues to flow. Once that potential difference has been reduced or eliminated, the driving force disappears and the current stops. Nothing has been destroyed or hidden beneath the earth. The system has simply reached a new electrical equilibrium, where there is no longer a reason for charge to continue moving. This principle explains what happens after current flows through a grounding system during an electrical fault. The grounding conductor provides a low-impedance path that allows fault current to return toward its source, enabling protective devices to disconnect the circuit. During a lightning strike, electrical charge spreads rapidly through the surrounding environment, redistributing itself across an enormous conductive network that includes the earth, metal structures, water, and utility grounding systems. In both cases, the process is governed by the same physical laws. Charge moves because differences in electric potential exist, and it stops once those differences have been greatly reduced. The Earth is not acting as an electrical landfill. It is participating in a much larger electrical system seeking equilibrium. Perhaps that is the most useful way to think about grounding. It is not a destination, but a reference. It does not consume electricity, store electricity, or make electricity vanish. Its role is to establish predictable electrical conditions and, when necessary, provide a safe path that allows dangerous fault currents to be cleared quickly. Nearly every modern electrical network, from a small household outlet to a continent-wide power grid, is built around this idea. Electricity always requires a complete circuit, and grounding exists primarily to ensure that when normal operation fails, there is still a controlled and predictable path available. Understanding that single concept transforms grounding from an everyday word into one of the most elegant safety principles in engineering, reminding us that the purpose of grounding has never been to make electricity disappear, but to make electricity behave in a way that protects both equipment and